Hi friends, welcome back to the channel Engineering Mathematics for GATE exam. In this video, I will give you the notes on vector calculus for GATE exam. And this is one more chapter in engineering mathematics for GATE exam papers. But this chapter is applicable to only some papers. For example, that is for agricultural engineering and for mining engineering and for metallurgy engineering. Students have this chapter in their GATE paper. Okay, so and the remaining students doesn't have this there in their syllabus, like computer science engineering students doesn't have this chapter in their syllabus. Okay, uh, and the content for the video is I will explain you what is meant by vector calculus, and I will explain you how to apply the gradient while solving the numericals on vector calculus, and how to apply the divergence on for vector calculus problems, and how to use the curl while solving the numericals on vector calculus, and what are various vector identities, and what is vector integration, what is surface integral, line integral, volume integral, and what is meant by Green's theorem, what is Gauss divergence theorem, what is Stokes theorem. Okay, that is the content for this video, and that is the exactly that reflects the syllabus for vector calculus in GATE exam. Okay, vector calculus deals with the differentiation and integration of a vector fields primarily in 3D space. So in order to do the differentiation and integration for vector fields in 3D space, you can use this vector calculus. Okay, vector differential operator del is written as del is defined by gradient. Okay, it is called as gradient. Let f of x comma b is a differential function. Gradient of f of x comma y comma z written as del f or grad f is defined by del f is equal to dou f by dou x I bar plus dou f by dou y z bar plus dou f by dou z k bar. Okay, del f defines a vector function. Clearly it is a vector function. If you look at the del f, it is clearly a vector function, vector quantity. Okay, if f of x comma y comma z is equal to 0 in is any surface, then del f is normal to the surface. Okay, and using this gradient, basically you can calculate the directional derivative. Look at how to calculate the directional derivative. The directional derivative of f of x comma y comma z at point p of x comma y comma z along a bar is del f at p dot a bar by modulus of a bar. Clearly it is a dot product, so you will get scalar quantity. Okay, so the directional derivative of f of x comma y comma z is maximum along del f, and the magnitude of this maximum is nothing but modulus of del f. Okay, now look at one example how to use the gradient in order to find the directional derivative. Okay, so example 1, find the directional derivative of function x square minus y square plus 2z square at p of 1 comma 2 comma 3 along z axis. Okay, so in order to identify the directional derivative, first you have to know the del f at p. So given function is x square minus y square plus 2z square. So after using the del operator, dou f by dou x is nothing but dou f by dou x is 2x, so 2x I bar minus dou f by dou y is 2y z bar plus dou f by dou z, so 2 into 2, so 4z k bar. Okay, so del f at p is nothing but 2x I bar minus 2y z bar plus 4z k bar at point 1 comma 2 comma 3, that is equal to, if you substitute point in the del f p, you will get 2 I bar minus 4z bar plus 12 k bar, and here it is clearly mentioned along x z axis. So the function for a bar is k bar because it is along z axis, so I bar and j bar coefficients are 0. Okay, so directional derivative is nothing but del f at p dot a bar by modulus of a bar, so 2i minus 4j plus 12k dot k bar dot square root of 0 square plus 0 square plus 1 square. So that is equal to dot product of these two vectors is clearly 12. Okay, so answer is 12. Now look at the next concept, divergence. If a of x comma y comma z is equal to a1i plus a2j plus a3k, then divergence of a can be written as del dot a bar, defined by del dot a bar is equal to dou a1 by dou x plus dou a2 by dou y plus dou a3 by dou z. Okay, so the properties of divergence, and clearly it is a dot product, so it is a scalar quantity. Okay, so the properties of divergence, look at first point, del dot a bar is a scalar function, it is a clearly dot product, so you will get the scalar quantity. Okay, now look at the point 2, del dot a bar is not equal to a bar dot del. Okay, and look at the point 3, del dot a bar is equal to 0, then a can is solenoidal. Okay, so in case in the question if it is mentioned solenoidals, and then you can apply directly del dot a bar is equal to 0 and find the required answer, required thing in order to find the solution. Okay, now look at point number 4, del dot del f is equal to del square phi. Okay, and del square phi is called as Laplacian equation, and del square is Laplacian operator. Okay, so remember these points in order to solve the numericals on vector calculus. These are very important properties and definition of divergence. Okay, now look at the questions how to solve the and vector calculus problems using divergence. Okay, so if example 1, if a bar is equal to x square y minus 2 xz z bar plus 2yz k bar, that find the del dot a bar at point 2 comma minus 1 comma 3. Okay, so del dot a bar is nothing but, so dou by dou x of x square y, that is equal to 2xy, minus dou by dou y of 2xz, because there is no y term, so it is treated as constant and 0. Okay, and dou by dou z of 2yz, so it will be 2z, sorry 2y. Okay, dou by dou z of 2yz is nothing but 2y. Okay, so 2xy minus 0 plus 2y at 2 comma minus 1 comma 3. So after substituting that point p here, you will get 2 into 2 minus 1, so minus 4, and 2 into minus 1 minus 2, so minus 2 minus 4 is equal to minus 6. That is the answer. Now look at the example 2. Determine the constant a so that the vector v bar is equal to 3x plus x plus 3y I bar plus y minus z z bar plus x plus az k bar is solenoidal. So in the properties of divergence, as explained clearly, solenoidal means del dot a bar is equal to 0. Okay, so apply del dot a bar and make it 0, then you will get the a. Suppose c, dou by dou x of x plus 3y is nothing but 1. Okay, because 3y is treated as constant, that will be 0, and dou by dou x of x is nothing but 1, and dou by dou y of y minus z is nothing but 1. Here also z is treated as constant, so that will be 0, and dou by dou y of y will be 1. Okay, and dou by dou z of x plus az, and x here x is treated as constant, so that will be 0, and dou by dou z of az is nothing but a. So 1 plus 1 plus a is equal to 0, because it is mentioned it is a solenoidal. So a is equal to minus 2. Okay, now look at the example 3. If phi equal to x square y cube z power 4, then find del square phi at 1 comma minus 1 comma 1. Try to solve yourself, you will get the answer minus 20. Now look at the another important concept in vector calculus is curl. Okay, the curl of function f of x comma y comma z, that is equal to a1 I bar plus a2 z bar plus a3 k bar, is a differentiable vector function. Then curl of a bar can be written as del cross a bar. Okay, basically it is written as, the curl is written as del cross a, whereas in case of divergence it is written as del dot a bar. Okay, there is dot product, here it is a cross product. Okay, so del cross a bar is equal to I j k dou by dou x dou by dou y dou by dou z. You have to write it in the form. Okay, a1 a2 a3. Okay, so that will be I bar into dou a3 by dou y minus dou a2 by dou z plus z bar into dou a3 by dou x, sorry, dou a1 by dou z minus dou a3 by dou x plus k bar into dou a2 by dou x minus dou a1 by dou y. Okay, so here it is clearly the vector quantity. So del cross a bar, that is curl, is a vector function. We will get the vector function. See, del cross a bar is a vector function. Okay, and if del cross a bar is equal to 0, then you can call it as irrotational. Okay, in case of divergence, what we said, del dot a bar is equal to 0, then we can call it as solenoidal. Whereas in case of curl, if del cross a bar is equal to 0, then you can call it as a bar is irrotational. Okay, now look at the example. How to solve? Example 1. Find constants a comma b comma c so that v is equal to x plus 2y plus az I bar plus bx minus 3y minus z bar plus 4x plus cy plus 2z k bar is irrotational. So it is clearly mentioned irrotational means we have to apply the cross product del cross a bar and we have to make it 0. Then you will get the desired answer. Okay, so given function is rotation, so del cross phi is equal to 0, so del cross a bar is nothing but ijk dou by dou x dou by dou y dou by dou z a1 a2 a3 is equal to 0. Okay, determinant of that, so dou a3 by dou y minus dou a2 by dou z, okay, is equal to dou a1 by dou z minus dou a3 by dou x minus is equal to dou a2 by dou x minus dou a1 by dou y is equal to 0. So dou by dou y of 4x plus 3c plus 2z minus dou by dou z of bx minus 3y minus z is equal to 0, and you will get the answer c is equal to minus 1. And dou by dou y z of x plus 2y plus az minus dou by dou x of 4x plus 3cy plus 2z is equal to 0. From this you will get a is equal to 4, and dou by dou x of bx plus bx minus 3y minus z minus dou by dou y of x plus 2y plus az is equal to 0. So b minus t is equal to 0, b equal to 2. Okay, so that is the way to apply divergence or gradient and curl. Okay, now look at the another important point concept, that is vector identities. If a bar and b bar are vector differential functions, f and g are differentiable scalar functions of position x comma y comma z, then the vector identities are, we have to remember these vector identities in order to apply or operate, or you can use while solving the questions, numericals. Okay, but these are the vector entities you have to remember. Del of f plus z can be written as del f plus del z. Okay, and del of f of g, del of fz is equal to del of f of del z plus z del f. Okay, del dot a bar plus b bar is equal to del dot a bar plus del dot b bar, and del cross a bar plus b bar is equal to del cross a bar plus del cross b bar, and del dot f of a bar is equal to del f dot a bar plus f of del dot a bar. Del cross f of a bar is equal to del f cross a bar plus f of del cross a bar. Point 7. Del dot a bar cross b bar is equal to b bar dot del cross a bar minus a bar dot del cross b bar. And point 8 is del dot del cross a bar is equal to 0. Okay, del dot del cross a bar is always 0. Okay, and point number 9, del cross del phi is equal to 0, that is del square phi is equal to 0. That is a Laplacian function we have seen already. Okay, point number 10, del cross a bar is equal to, that can be written as del of del dot a bar minus del square a bar. Okay, note point number 1, if a bar and b bar are rotational, then a bar cross b bar is solenoidal. Okay, so remember these points, these are very important. Okay, while solving the numericals, if a bar and b bar are rotational, then a bar cross b bar is solenoidal. If f and g are differentiable scalar functions, then del f cross del z is solenoidal. Curl of phi, gradient of phi is equal to 0. Okay, so that is the important properties you have to remember points. Okay, now look at the vector integration. First one is line integral. In general, if any integral which is to be evaluated along the curve is called the line integral. Let r bar is equal to xi bar plus yj bar plus zk bar be the vector of any point x comma y comma z on a curve C joining the points p1 and p2. Assume C is composed of a finite number of curves for each of which r bar of u has a continuous derivative. Okay, let a bar of x comma y comma z is equal to a1 I bar plus a2 j bar plus a3 k bar be a differential vector function. Then the integral of tangential component of a bar along C from p1 to p2 is integral of p1 to p2 a bar dot dr bar is equal to integral of p1 to p2 a1 dx plus a2 dy plus a3 dz. That is a line integral. Now look at some important points regarding line integral. If a bar is the force on a particle moving along C, this line integral represents the work done by the force. Okay, if C is a simple closed curve, then the integral around C is often denoted by circular integral of a bar or dr bar. Okay, in aerodynamics and fluid mechanics, this integral called the circulation of a about C, where a represents the fluid velocity. Okay, and if a bar is equal to del phi, that is del cross a bar is equal to 0 in a region R of space, then these you have to remember these 2 points, that is integral of p1 and p2 a bar dot dr bar is independent of path C joining p1 and p2 in R, and the next point is circular integral of a bar dot dr bar is equal to 0 around any closed curve C in R. Okay, now look at the next important concept, that is surface integral. If S is a piecewise smooth surface and f bar, that is f x comma y comma z is a differentiable vector function, yes, let p be any point on S and let n bar be the unit vector at p in the direction of outward drawn normal to the surface S at p, then double integral of S f bar dot n bar ds is an example of surface integral. Okay, so surface integral of a bar dot n bar ds is equal to that double integral of s bar s double integral of surface integral a bar dot n bar ds dx dy divided by dx dot dy divided by n bar dot k, where r is the projection of s in xy plane. Now look at next concept, volume integrals. Consider a closed surface S enclosed in a volume V, then volume integral, that is triple integration of a bar dv, and volume integral phi dv, that is triple integral of phi dv, are examples of the volume integrals. Okay, so line integral is a single integral, and surface integral is a double integral, and volume integral is a triple integral. Okay, now look at how to apply these line integral, surface integral, and volume integral in the vector calculus. Okay, look at first one, the Green's theorem. Okay, if R is the closed region of the xy plane bounded by a simple closed curve C, and if M and N are differentiable functions of x and y in R in the region R, then integral of mdx plus ndy is equal to integral of in the region dou n by dou x minus dou m by dou y is equal to dx dy. Okay, basically it is the Green's theorem gives the relation between a line integral of a line integral around a simple closed curve C and a double integral over the plane region R bounded by C. Okay, now look at and where C is the transferred in positive direction. Okay, now look at next theorem, that is Gauss divergence theorem. Okay, if V bar is the volume bounded by a closed surface S and a bar of x comma y comma z is a differentiable vector function, then surface integral a bar dot n bar ds is equal to volume integral of del dot a bar dv, where n bar is a positive normal to the s. Okay, so basically Gauss divergence theorem is it relates the flux of a vector field through a closed surface to the divergence of the vector field in the volume enclosed. Okay, so it is clearly surface integral and volume integration, application of surface integral and volume integral. Okay, the Gauss divergence theorem, whereas Green's theorem is the application of line integral and surface integral. Okay, next one is Stokes theorem. Let S is an open two-sided surface bounded by a simple closed curve and a bar x comma y comma z is a differentiable vector function, then circular integral of a bar dot dr bar is equal to surface integral of del cross a bar dot n bar ds, where c is transferred in the positive direction. So Stokes theorem says the surface integral of curl of function over a surface S, okay, is equal to the circulation of the function f around the boundary of the surface. Okay, so it is the application of circular integration, the line integration, surface integral. Okay, now I will upload the numerical questions on vector calculus. Try to solve yourself. If you have any doubts, you can ask me in the comment section. Thank you for watching. Please do subscribe my YouTube channel for more videos, and please do refer my YouTube channel to your friends. Thank you for watching.